In this video, we describe how to write the electronic configurations of ionic species. We're going to be discussing this in the concept of chemical bonding. And what we know is that when atoms form bonds, they tend to acquire electronic configuration of a noble gas. We're going to focus now on ionic bonding, which is produced by a metal and a non-metal. And what we know is that usually the non-metals tend to form negative ions when they form ionic bonds, and then the metals tend to form positive ions. And again, the ultimate reason for this is that these elements, by gaining electrons, are able to acquire noble gas electronic configuration, and these elements, by losing electrons and becoming positive ions, are able also to acquire noble gas configuration. Alright, so for example, let's take a look at the calcium oxide ionic compound and try to write what the electronic configurations for the constituent ions are. Right, so calcium oxide has this formula and is formed by the electrostatic interaction of calcium 2+ ions and oxygen 2- ions. Right, we go to the periodic table and write the electron configuration of calcium, and this is going to be equal to argon 4s2. And then for oxygen, the electron configuration is going to be that of helium, and then 2s2, 2p4. Right, so the formation of the calcium 2+ ions involves the removal of 2 electrons, and then we see that that makes perfect sense from the electronic configuration, right? If we remove these 2 4s electrons, then we form the calcium 2+ ion, and that calcium 2+ ion has the same electronic configuration as argon. Okay? Conversely, when we look at oxygen, if we were to add 2 electrons, then you would actually have the 2- ion, and then this would be exactly the electronic configuration of neon. Okay, so it's pretty easy to see how metals and non-metals have charges, right? When they form ions, they have charges that generate ions that have noble gas configuration. Okay, this is very common when you think about main group elements. Okay, so the non-metals will be right here. That's the main group for non-metals. That will be the main group for metals. The question is what happens with transition metals. And in transition metals, the way to form ions is a little different. Okay, for example, let's take a look at the case of manganese. Okay, so manganese has an electronic configuration of neon, and then 3s2, 3d5. Okay, so it's very common in transition metals that when you start to remove electrons to form positive ions, and that's what these metals want to do, the first electrons that are removed, okay, the electrons that are easier to remove are actually the s, not the d. Okay, so when we actually form the magnesium 2+ ion, okay, the 2 electrons that actually are removed are the 2s ones, the 3s ones, and then the resulting electronic configuration of the ion happens to be 3d5. This removal of the s before the d is actually connected to the values of the ionization energies, and ultimately that is related to the way that those electrons are differentially attracted to the nucleus. And concepts like shielding and penetration, electronic repulsion are all involved in that distinction. Okay, but the operating rule is that when you're forming ions of transition metals, then the s electrons have to remove first prior to the d electrons. Okay, so in this video we actually have seen how to write electronic configurations for ions. And again, the leading theme is that when you're looking at main group elements, those atoms tend to form ions that let them reach electronic configurations of noble metals, of noble gases. Now, when thinking about transition metals, we have s and d electrons, and it turns out that those metals tend to form various types of ions. Okay, but in any case, the electrons that are removed first corresponds to the s shell, not to the d shell.